Hey guys, all right, so this last video is about graphing trig functions. We're going to eventually do all six, but I'm going to start off with just sine and we'll look at what happens to the trig function because technically the way that things are affected for the sine graph are the same for cosine or tan or cotan and the rest of them. So we're going to go pretty in depth with this sine graph and then we'll talk about how that relates to everybody else. Okay, so first of all, see how we have this function, this is the sine graph. You've probably seen it before last year, and it has something called periodic motion, or it's a periodic graph. And that means it basically repeats itself over a certain period, right? So it has a repetitive nature to itself. So first of all, if you want to see one period would be the amount of time or x-axis distance it takes to repeat. So this guy, its whole cycle takes that long. So right there, this is a wavelength, or we could call this a cycle, right? Okay, so that's it, or you can call it a period. That's the period of the graph, that's where periodic comes from. That's how long it takes to finish one cycle. Okay, so that's a period. We also have something called the amplitude, which the amplitude is the height of the wave. So the distance from the x-axis to the top of the wave is the amplitude. Notice I didn't say from high to low. That's different, right? From high to low would actually be double the amplitude. So you go up as much as you go down, but the amplitude is technically just from the y-axis to the top of the wave. So that's the amplitude or the height of the wave. Okay, and so there are going to be things that affect those two values. There are going to be things that affect how long the wave is, how tall the wave is, and technically also where the wave starts. Meaning like this is on the x-axis, which is beautiful, but sometimes that can be shifted up or down or left or right. So that's what we're going to look at today. We're going to look at how does this graph shift. Okay, so the first one we're going to look at is what happens if I take this function. Now I know this has an x, but technically that x is an angle. So if you want to think of it as this instead, you could. So remember, we're plugging in angles and we're getting outputs. If you're trying to figure out how this graph is graphed, you can think of it like this. The sine gives you the y value on the unit circle, right? So like if I go over here to 0 radians, my y value is 0. If I go to pi over 2, then my y value here is 1. So check it out, 0, 0. If I go, this is about pi over 2, about 1.5, I'm at 1. If I go all the way around to pi, my y value goes back down to 0. So there we go. So see, this is just tracking the point using the y value. So it's saying y is 0, then it goes up to 1, then down. So it's doing the vertical change, right? And then it graphs it. So here's the top half of the circle, kind of the bottom half, and then it keeps repeating because you'd keep going around and around. So you guys, again, should have been introduced to this last year, but just in case you weren't, there you go. Okay, so let's see what happens if I start changing this function, augmenting it. So the first thing I'm going to look at is what happens if I multiply by something out front. So let's do that. So in this picture, I have sine of x, which is in purple, and then I have 3 sine of x. So I'm multiplying by a value out front. Okay, for the second guy. So what did happen to the graph? Everything looks the same except what? Yeah, the amplitude looks different, right? So the amplitude was affected. In fact, check it out. The amplitude for this wave, the regular wave, was 1, but the amplitude for this wave was 3. Interesting. Let's look at another one. Let's try, I'm going to graph one where it's 0.5 out front, and I want to show you guys this. If you go all the way to the left and you hit enter, you can change the way your graph looks. Like this is the plane line. Notice down here I hit enter until I got to something bold, and then this one is a dotted line. We'll mess with those a little bit. Make sure you're in radian mode. So I went to mode and I am in radians. I'm going to go back to y equals, and then I'm going to hit zoom trig. Zoom trig gives you the best window that's going to make your trig graphs look nice. So zoom trig is where I'm going to start. Yeah, look, there it goes. So there's the original. There's 3 sine x. That was my second graph. And then the last one I did was 0.5. Aha. So the height or amplitude of my wave went down to the max height was 0.5, which might have been exactly what you expected. So when I did half sine x, my amplitude was only 1/2. So it looks like when I have a number out front, it's affecting the amplitude or the height when I'm multiplying by something out front. Okay, let's see what happens when I multiply by something on the inside. So here I have sine of x in the purple again, and then I have sine of 2x in green. Let's see what happens. Well, the amplitude didn't change, which we shouldn't be surprised about because nothing was multiplied out front. But by multiplying by something on the inside, the period definitely changed. Okay, so let's look. The old period used to go from here to here. So that used to be that's the period of just plain old sine. What do you notice the period is for the green graph? Well, it looks like it only takes half the distance to go that full period. Do you guys see that? It takes half of the whole thing. That's one way to think about it. So you could think about it like that, or how many of these waves or cycles fit in the old period? 2. So that's another way of talking about that. So its frequency is 2, meaning that there are now 2 waves in what used to be 1 period. So that's how it matches up perfectly. If you want to know the actual period, though, you have to take the original function's period and divide by this number. So, and I'll go through this again in a little bit, but I would take the original function's period and I would divide by this value. So in this case 2. So let's look at another one. Let's look at what would it be if I divided by 4x. Well, or I'm sorry, if I multiplied by 4x. Well, we would expect to see, I'm going to make it a little bit bigger, viewer. We would expect to see it, if I multiply by something bigger inside, have even more waves. So let's look. So I'll do sine of 4x. So according to what we just said, we would expect now to see 4 waves that fit in the 1 period. So let's look. There goes my original. So there's 1 wave. Let's see. Whoa. All right, let's count. Whoops. Sorry, I lost him. Let's count. We've got 1, 2, 3, 4. That used to be the 1 whole wave. See that? So there's 4 waves. Or if you just want 1 period, it's now 1/4 of what used to be the whole thing. So we can see that when I multiply by a value on the inside, I'm affecting horizontal like stretching and shrinking, right? So just again, one more time. Multiplying on the outside affects my outputs, so it affected my vertical stuff. And then multiplying by the inside affected my x values, which affected my horizontal stretch or shrink. Okay. Okay, so we have both of those. Let me see if I did. Yeah. Okay, so then what do you think would happen if I add something? Well, this one I think should make sense, guys. If you have sine of x and you add 3 on the end, it won't affect what you plug in for x. That's not going to change. It'll just add 3 to your sine value. So if I add 3, that's going to just increase my y value by 3, which means every one of these y values gets shifted up 3. What do you think would happen if I subtracted? Whoa, hello. Yeah, if I subtracted, I just shift down. So again, you could try this out in the calculator. I'm going to go in and erase this. So I could show you doing like sine of x, plus 2. You would assume that that would move the graph up 2. Or I could do sine of x minus 4, and you would assume that would shift it down 4. So let's take a look. There's the original. The next one should shift. Yep, there it goes. See, it's up 2. All the points are the same, just up 2. And the last one was shifted down. Can't see it all because it goes off the graph, but it's all down 4. So adding and subtracting something on the end affects the y value, which means it's going to shift it vertically. So it'll shift it up and down. Again, I'll refer to all this at the end. And then last but not least, the only thing we haven't done, what happens if I add or subtract on the inside? Well, once again, guys, if you do something to the inside, you're affecting the x first. So when I add or subtract on the inside, it shifts me left and right horizontally, as you can imagine. I mean, you probably would have predicted that. So the blue is my original graph, right? And then the red is my new horizontally shift graph. Okay, and you probably talked about this before when you did like quadratics. Remember this? When you did like, x plus 2 squared plus 7. Remember this when you were comparing that to like a parabola? You would say, oh, this went up 7, but remember how this was always the opposite? So this would be like, oh, instead of even though I'm adding 2, I'm technically going left 2. Remember that? Same thing applies. This actually shifted right 2 pi over 3. And as we do more with this graphing, you guys will get to see that. Okay, so let's bring it all together. Let's talk about everything in one spot here. Okay, so let's make some general relationships. So in this the first thing I want to do is I want to write this, but I want you to understand what I'm doing. So I'm writing all of these transformations apply to any trig function. So I'm writing the word trig, but I really mean sine, or this could be cosine, or this could be tan. So first thing I would want you to do is write this down. So we've got y equals, we've got a. We're going to use that variable out front. Then we have our trig function. So this could be the word, cos or tan or sine. Then I have b. And then I used lowercase, so I'm going to change that to a lowercase. Doesn't really matter. And then I like to use a parentheses, so I'm going to change this up to a parentheses. And I'm going to do x minus c plus d. So I'm changing this slightly. There we go. Okay. So now over here, I'm going to talk about what the different things do. So we already said this. We said a affected our function how? It was a change. It was a vertical stretch or shrink. Changed amplitude. So a is a change in, it's the amplitude. Well, technically it's the absolute value because I don't care if it's negative. We'll talk about the negatives in a second. So the absolute value of a is your amplitude of your wave, or the height of your wave, right? You can also think of it as a vertical stretch or shrink. And then before I go away from that, what happens if it is negative out front? You should know this from last year. Like if I had y equals x squared versus negative x squared, what happened to that graph? Yeah, the negative out front just reflected it over the x-axis. Guess what, guys? Same thing here. If I have a negative a value, the negative has nothing to do with how tall it is, but a would tell you if it's been reflected. So I'm going to add that over here. If a is less than 0, which means negative, then it's reflected over the x-axis. Okay. Okay, for b was multiplying by a number on the inside. So we said, once again, I'm going to do the absolute value. B affects the period. Okay. And it is a horizontal stretch or shrink. Okay. B is also the frequency. Because like if this is a 2, we said there'd be 2 cycles. There's the cycle happens twice. So that has a frequency of 2. But if B is negative, right? We did this also last year. If you have a negative inside of your function, it flips it over my other axis. So if b is less than 0 or negative, then you have a reflection over the y-axis. Okay. All right, and then C and D are really easy. C and D, adding or subtracting to the X shifts you left or right. So C is a horizontal shift. And again, because technically the equation has a built-in negative, it's the opposite of what you think. So if you see it being, so this is left or right. So if it looks like a minus, it's actually going to the right. And if it looks like a plus, it's actually going to the left. And then D shifts me up and down. So vertical shift. This one's straightforward because it is a plus. So if it's up, if it's a positive number, you went up that much. If it's negative, you go down. Okay. So this is the general effects that can happen on a graph. Okay. So now to actually be able to graph these, we have to look at the specific graphs themselves. So that's the next thing that I'm going to do. I'm going to look at some specific graphs. And when I do that, these are the things that I'm going to use. I'm going to use a given equation, and then I'm going to use, I'm going to identify the values. I'm going to make it a little smaller here. I'm going to identify the values, and then I'm going to use that to help me graph. Okay, so we'll start with something fairly easy. Well, first of all, we'll start with sine. So the sine graph, we'll do the equation y equals, we'll do 2 sine of x plus 5. We'll keep it real basic for this first one. So A is 2. So I should always identify, I don't have, B is just 1. So there's really no change to B. There's no change to C. And D is 5, up 5. So that means my amplitude, remember, I think it's important to remember what it is for sine, the original sine function, so that you can graph the new one. So sine originally has a period, this is important, of 1 time around the circle, which is 2 pi. So this is true for sine and cos. So sine and cos both have a period of 2 pi, and they have amplitudes of 1. Okay, so that means my new amplitude would be 2. A. My circular frequency is still just 1. My period, now the way that you get your period, you should write this down. The way that you solve for the period is you take the original period and you divide by your b. Well, my original period for sine is 2 pi. It used to always be 2 pi. But since b is just 1, dividing it by 1 wouldn't change it. So the period stays the same. Okay. To be able to graph these functions, this is a big, I'm starting something big here. We graph what are called the 5 critical points. The 5 critical points are, for sine, are this point that's at 0, 0. There's a point that is halfway through at 0, and then a point all the way at the end of the period that's at 0. So, or equilibrium is another way. You're going to hear me call it that a lot. It's kind of that equilibrium line. Okay. And those are evenly spaced out over the period. Then, halfway between these two, you're at the highest point of the wave, and halfway between these two, you're at the lowest point of the wave. So see how we have these 5 critical points? So each of them is, if I start here, this next one is 1/4 of the way through the period. So if I take a fourth, for example, of 2 pi, that gets me pi over 2. This distance is what we call a step, because that's like the next critical step. So if I go a step, I go up to the top. Then if I go my next step, I go back down to equilibrium, then down, then my next step, and so on and so forth. So a step should be 1/4 of your period. So for this particular problem, it's 1/4 of 2 pi, so pi over 2. So my period doesn't change. My vertical displacement is just if you shift it up or down. So that would be your D value. So yes, my vertical displacement is I went up 5. Phase shift is a fancy way of saying C, and I didn't have a phase shift, so there was none. So now starting point and end point, we'll figure all that out as we go to do it. Okay, so let's actually graph this guy. Okay, so when we graph these, I start by graphing I graph my new equilibrium. So equilibrium is 0, and then if you shift up, your equilibrium is going to go up that much, or if you shift down. So the first thing you want to do is draw your little graph, and I'm going to mark where my new x-axis is, if you will. So this whole graph got shifted up 5. So I'm going to go 1, 2, 3, 4, 5. So there's my new equilibrium. And if you want, you could draw a little really light line on your graph at 5. Okay, then I like to draw my high and my low. So I'm going to go my amplitude from there. So my amplitude is 2, right? So that's the height of my wave. So I'm going to go 2 up, which would get me to 7, and I'm going to go 2 down, which would get me to 3. And again, if you want to make little light lines on your graph, these little, oops, I missed on this one. These little guidelines can kind of show you where your graph is. Okay. Then after I do the y-axis, I always do the x-axis. So the x-axis is pretty easy. The first thing you would do is figure out if you need to shift it all, right? But we don't have a phase shift. There's no shifting left or right. So we're going to start at 0. So my graph is going to start right here. We'll do harder ones in a second. Then I need to know what my period is. So my period we said was 2 pi. And I need to know how much my steps are. So my step is pi over 2. And so my graph I need to be able to move in chunks of my step easily. So I'm going to go pi by pi over 2. So I'm going to go pi over 2, another pi over 2, which would just be pi, another pi over 2, 3 pi over 2, another pi over 2, which would be 4 pi over 2 or 2 pi. And there's a full period. So there's the beginning of my period, there's the end of my period. Okay. So now we can graph sine. Remember, sine at the beginning of its wave should be right on equilibrium. And then I like to do this. At the beginning, it's at equilibrium. Halfway, it's at equilibrium. At the end, it's at equilibrium. Then halfway between these guys, which is at this step, it's up at the top. Halfway, it's at the bottom. And then I can just connect. And if I wanted to make another period, then I could just keep going. So I could go 4 more of these steps, which would be, let's see, these are technically by halves. So this is 1, 2, 3, 4. This would be 5 pi over 2, 6 pi over 2, which is really 3 pi, 7 pi over 2, 8 pi over 2, which is really 4 pi. So that would be, I went 1, 2, 3, 4, my new steps, and then you just literally repeat. So here, then I go up for my next step, then I go down, then I go way down to the low, then back up. Okay. So my starting point, once you have your graph, it should be easy. My starting point was right here, and that was 0, 5, because I can tell because I marked my axis. My ending point of my one period was right here, which was 2 pi, 5. No asymptotes. Okay, let's try another one. I think I'm going to need a clean screen, so I'm actually going to get rid of this. Okay, so let's try one that's a little bit busier. Let's do y equals, we'll do 3 sine of 2x minus pi over 3. Yeah, we're not messing around on this one, right? Minus 4. Okay, so the first thing that I would do is find out what my A, B, C, and D are, right? So A is 3, B is 2, C is pi over 3, and D is minus 4. So what does that mean? Well, that means my amplitude is 3. If my B is 2, figure out your period. That should be the next thing you do. Remember, I take sine's original period, which is 2 pi, and I divide by 2. So now my new period is pi, so my whole wave will fit in pi. My shift is pi over 3, okay? Now, you need to figure out your step, and remember, your step is always a fourth of your period. So each step needs to be pi over 4. Now, this is crucial, guys. All of your horizontal stuff, your step, your phase shift, and your period have to be able to work together because this is all the stuff affecting horizontal. So that means I need to get these all into fractions that work together. That's the easiest way to do this. So let's see. If I have fourths and thirds, the easiest number that they both go into is twelfths. So I'm going to put all these guys into twelfths. So multiply by 3 on top and bottom. So each step will be 3 pi over 12. The shift will be 4 pi over 12, and the period will be 12 pi over 12. So see, I just changed each of those into twelfths. It makes it much easier. So now each of my little tick marks is going to be a pi over 2. So, okay, so then do your phase shift first. So I'm going to go over to 4 pi over 12. So 1, 2, 3, 4. And I'm going to mark it. There's my first, that's going to be the beginning of my period. I have to mark my phase shift. Okay, then we can do what we need to do. So then I can go my whole period if I want. So my whole period is 12. So from here, I'm going to go 12. Whew. Okay, so I counted 12. Let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, but remember, I'm adding 12 to 4 pi over 12. So if I added 12 to that, that would actually get me to 16 pi over 12. Now you can leave this 16 pi over 12 for right now. We can totally reduce that, and I can reduce this too, but I'll wait for now. So there's the beginning of my period. There's the end of my period. And then let's get our y-axis. So our y-axis, our equilibrium line, is now at -4. So our x-axis has shifted down to -4. So there's your your new x-axis. And then my amplitude goes up and down 3. So if I go up 3, my highest would be at -1. And if I go down 3 from here, my lowest would be at -7. So there's my highest my graph should go, and there's my lowest my graph should go. So my graph should fit right in that beautiful little box. You won't always have to draw the box in the future, but if that helps you for now, do it. Okay, so this is a positive sine graph. So this graph is going to go up, start at equilibrium, go up, and then come back down, and then come back up. So at the beginning of its period, it should be at equilibrium. So I'm going to put that little guy at -4. Okay. Then I'm going to go 3 of my little units because that's my step. So when I go 3 of my little units, I should be right here at the top of my wave. So 1, 2, 3, I'd be at the top of my wave. Go your next step, 1, 2, 3, you're back down at equilibrium. 1, 2, 3, you're at the bottom. 1, 2, 3, you're back up at equilibrium. I'm graphing these 5 critical points. Once I have them graphed, I can connect them. There's my equation. Graphed. Now, if you needed to identify these points, you could use your axis. Like, for example, this starting point reduced is pi over 3, comma, -4. This point, count from the beginning, 1, 2, 3, 4, 5, 6, 7 pi over 12, comma, -1. See, you can get everything that you need to get your coordinates, and I could keep going. Okay, so that one was a little bit busier. All right, let's look at what if it was a negative sign? I think I might make this video 2 videos because otherwise I think it's going to be pretty long. I'll do sine and cos first, and then I'll do another video at the beginning of next week. Okay, so what if it was a negative sign? So let me do one that's negative. So we'll do and we'll do like a weird number out front. So we'll do 0.2 negative, excuse me, 0.2 sine. Let's do 4x plus pi. I changed my mind. Let's do 4x plus 3 pi. And then let's say plus 1. Okay. So I don't know if you noticed in this problem, but I didn't factor out b. If it's not factored, the first thing you should do is factor out that b, which means I have to divide by 4 to pull it out. So if I divide by 4 from each term, this term would become a 3 pi over 4. Remember, when you factor it out, you're dividing it out. So I'm dividing that. There, now you can see what your A, B, C, and D are. Okay, so A is clearly, technically it's negative 0.2, but I'm going to say it's 0.2 for my amplitude. And what did a negative do again? That's right, it reflected over the x-axis. So your sine graph, instead of looking like this, instead of starting at equilibrium and going up, guys, is going to start at equilibrium and go down first, then come back up. That's all that happens. It's all that changes. So instead of going up first, when it's negative, you go down first. Start at equilibrium and go down. Okay, let's see, what do we have? We found that our b value was 4. So that means my period, remember your period then is 2 pi, which is the original period, over 4, so pi over 2. So my period is pi over 2. My shift is, careful, since it's plus, it's actually negative 3 pi over 4. Remember, it's the opposite sign. And then my d value is 1. I'm going to shift up 1. Okay, the only other thing that you need is your step. And remember, your step is a quarter of the way through the period, so it's a fourth of my period. So I'm going to take a fourth of pi over 2. So my step is actually a pi over 8. Oh my goodness, this is going to be some crazy stuff. Let's look, because remember, your period, your phase shift, and your step all have to be in the same units. Well, this one actually isn't too terrible because halves and fourths and eighths all go into what? Like, what's their lowest common denominator? Eighths. So the step can stay the same, but these two guys are going to change. So this, if I change this to eighths times 4 would be 4 pi over 8. And if I change this to eighths would be negative 6 pi over 8. Okay. So I always start with my phase shift. If there's a phase shift, I start there. So I'm going to shift to the left 6 pi over 8. So again, by doing this, I'm going to say my x-axis is going to go by pi over 8. So I'm going to go 6 of them to the left. 1, 2, 3, 4, 5, 6. So there's my negative. I know it's not reduced. That's okay for now. Okay, again, that's the beginning of my period. Okay, then my full period should go 4 of them. So 1, 2, 3, 4. That would put me here. But remember, if I'm actually marking that, that would be negative 2 pi over 8 on the actual x-axis because I have to count from here. Okay. And then let's see, my step should be, yeah, pi over 8. See, because I went 1, 2, 3, 4 of them. So, yep, we're good. Okay, now let's do our y-axis. My y-axis shifted up to 1. You always want to do your d value first. So it shifted. It doesn't really matter how big I make it. So I'm going to say that 1 is here because my amplitude should go up 0.1 or 0.2. So I'm going to add 0.2, which would go up to 1.2, and then go down, which would be 0.8. This doesn't have to be to scale, guys. So my equilibrium is now up at 1, my d value, and then I go up and down 0.2, which takes me up to 1.2 and 0.8. So this is why I really like to draw my own graphs, because then I can control the scale. So my graph should fit here. All right, let's do it. Remember, sine at the beginning of its wave is always at equilibrium. And then the only thing that changes is because this was a negative, don't let yourself forget it's a negative, I go down instead of going up. So each step I'm going to move is a pi over 8. So I'm going to go down first, then up my next step, then up to the top, then back down. So it looks like my sine graph just upside down. Okay. We are going to talk about domain and range. As you guys know, the sine and cosine graph go on forever. So both sine and cosine have a domain. That's easy. The domain is all real numbers. So you can say all reals, or you can say negative infinity to positive infinity. I prefer this, but it's okay. The range will be dictated depending on the high and low of your wave. So like you can look at your y-axis. My range would go from, in this one, 0.8 to 1.2, right? Because you're just going from your low to your high. Sine and cos are easy. The other ones get a little crazy. Okay, so let's look at the cosine graph because we got to do that guy. So cosine, all the ways that we mess with the graphs are the same. That's the best news. All you have to know is, what does original cosine look like? So what does just plain old cos of x look like? Well, plain old cos of x looks like this. At 0, x at 0 on the unit circle, guys, your x value is actually 1. So at 0, I'm 1. So that's different. Sine started at equilibrium, but cosine starts up at 1. Then when I rotate to pi over 2, I actually have x equals 0. So it goes down, and then it keeps traveling like this. So cosine starts at the top of its wave, goes down to the bottom halfway, and then comes back up to the top. So this is what positive cosine looks like. And as you can imagine, if positive cosine starts at the top of its wave and then goes down and comes back up, negative cosine would start at the bottom of its wave, go up, and come back down. So we'll do a positive one first. All right, so we're going to go crazy because now you guys know how to do this. So let's do 5 cos of, I'm going to do a fraction this time. 1/2 x minus 3 pi plus 2. Okay. Nothing changes about what I do to begin with. So first I would factor out the 1/2. Now careful, dividing by 1/2 doesn't give me half of 3. It actually ends up multiplying by 2. So this would become minus 6 pi. If you're not sure if you did it, multiply it back out. See, 1/2 of 6 does give me negative 3. Okay, so my A value is 5. My amplitude is now 5. My B value is 1/2, which means careful. If I want the period, I take 2 pi, because cosine also has a period of 2 pi, just like sine, and I divide it by the 1/2. Uh-oh, my period is now 4 pi, because dividing by a fraction is multiplying by the reciprocal. Phase shift ended up being, careful, a minus is actually 6 pi to the right, so positive 6 pi, and then my d value is 2. Okay, and then my step is a fourth of my period, so a fourth of, oh, hey, this one isn't so terrible, right? Because your period is in terms of pi, your shift is in terms of pi, and your your shift is in terms of pi, your period is in terms of pi, and so is your step. You don't have to change anybody. So that means I can go by pi on my x-axis. Sweet. Okay, so the first thing I'm going to do is my phase shift. So I'm going to go 6 of them. So there I am, 6 pi. That's going to be the beginning of my period. And then I need to go a total of 4 pi. So 1, 2, 3, 4, which would land me at 10 pi. Okay, so there's my beginning and end. Each step is pi. We already know that. And then let's do my y-axis. So my y-axis is I shift up 2. So I'm going to go, my x-axis is going to shift up 2. And then from there, I'm going to go up and down 5, which would be 7. And 1, 2, 3, 4, 5, which would be -3. So there's my high, my equilibrium, and my low. So here's going to be where my little graph is. So for cosine, remember, for a positive cosine, you start at the top of the wave. So the top of my wave is up here at 7. Then I go to equilibrium. So the next step is at equilibrium. Then I go all the way down to the bottom. Then I come back up to equilibrium, and then I go all the way up to the top. So the critical points are high, equilibrium, low, equilibrium, high. And then we're just making nice, beautiful, smooth curves. So remember, I get people who will draw this, right? No, these guys are smooth curves as you come. It's like a little valley and then a little peak. Whoop, see? Okay, so this shouldn't hit this at a sharp line. It should be curving softly towards it. Now let's just say I wanted to work back. I wanted to do another cycle before it. So if I wanted to go back, I just have to count the period. 1, 2, 3, 4. So the next period would go from here to here. And you could just repeat the process. Start at the top, equilibrium, low, equilibrium, high. And you could copy another period. Now my tick marks aren't perfectly evenly spaced, so that's why it looks a little different. Okay, let's talk domain and range. Domain, all reals, that's easy. Okay, my range would be y is equal to, let's see, my lowest y value is -3, and it goes all the way up to 7. Cool. All right, we'll do one more cosine graph, and then I'll call it a day for this. And then in the next video, I'll do the other trig functions, because you guys need a little practice with these guys first, I think. Okay, so let's do y equals, we'll do -3 cos. We'll do, well, no, I won't get crazy on this yet. Let's do cos of, let's do, well, I'll do 5. 5x plus 3 pi. I keep using 3. I'll do 2. 5x plus 2 pi. Minus 4. If you want to stop the video, try it, and then come back, you could do that. Okay, the first thing I would do, though, is to factor out the 5. So I'm going to divide them both by 5. Then I would start labeling. A is 3. The negative just means that my graph is going to, instead of starting at the bottom, at the top, it's going to start at the bottom and then come back down. So that's what the negative is doing. My b value is 5. So to get the period, I'm going to do 2 pi over 5. My c value, since it's at plus, it's actually a negative 2 pi over 5 because I'm going left, and my d value is -4. My step should be a fourth of my period, so a fourth of 2 pi over 5 gives me pi over 10. Now remember, those 3 horizontal things have to work together. So that means I can put them all in tenths. So that's what I'm going to do. Times 2 times 2, and times 2 times 2. Okay. So now I'm ready to do it. So I'm going to start with my phase shift first. Okay. So my phase shift is going left 4 of these pi over 10. So 1, 2, 3, 4. Pi over 10 is the beginning of my period. And then from there, I'm going to go my full period. 1, 2, 3, 4. Oh, that happens to land on 0. How nice is that? Okay. So each pi over 10 is my step. Okay. My y-axis shifts down to 4 first, so I have to do the equilibrium change first, so down to -4, and then my amplitude is 3. So I'm going to go up 3, -1, and down 3, -7. So top, middle, bottom. All right, let's graph this thing. Don't forget it's negative cos. If it was positive cos, we'd start at the top, but it's negative, so we reflect it, so it starts at the bottom. Then my next step goes up to equilibrium, then all the way up, then equilibrium, and then back down. And I do my nice smooth peaks and valleys, right? Okay. Domain, obviously all reals. And my range would be y equals, my low is -7 all the way up to -1. Okay, I think that you guys can do this. Again, I'm not going to overwhelm you, so I'm going to actually hold off on doing the tangent. I'll assign that on Monday night, and then we can do like tangents, cotangents, and stuff like that. But we'll start with this, and you can do some of those homeworks. So take your time. Really make sure you look at these graphs and how I did that. I think you've done this already from last year, so this shouldn't be too bad. But good luck with that, and I'll see you in class.